Hello everyone, my name is Oleksandr Pyvovar. I am machine learning engineer at Meta, and today we are going to talk about why good models fail in the production and how to build a system that. So imagine a situation, you train a model and your model achieved 95% accuracy in the lab. So now you deploy it with a confidence, but 6 months later its performance barely better than random guessing. And you think, what happened? And unfortunately, that scenario is not a rare exception, and industry report that 87% of data science projects never make it to production. And those that do, many of them fail silently. So today we're going to talk about the core failure modes, and deep dive into the why model fail. We will talk about the monitoring framework, how to build our instrumental panel, what exactly we want to monitor, the remediation playbook, how to fix what's broken, the best model retraining scenarios, and the principles of the production machine learning. It's a best practice for success. And we will move beyond the theoretical and dive into the practical challenges of production machine learning. So, talking about the core failure modes, we will cover data drift, concept drift, label drift, feature pipeline degradation and train serve skew, and feedback loops and PS amplification. And now, let's go to the first failure mode, data drift. So imagine you train a self-driving car, and you do it exclusively on the sunny and clear days. And now you want to deploy it in a city famous for its rainy and foggy weather. And suddenly the performance of your car drops. It's because that the images that car's camera received is different from what was used in a training data. This is a data drift in a nutshell. The real-world example is Zillow buying failure. So in 2021, Zillow automated home buying division, Zillow Offers, collapsed, leading to the staggering almost $1 billion loss and layoff of 25% of its workforce. And of course, the multiple factors were in play, but the main failure was because of the pricing model. It failed to adapt to the unprecedented market volatility and the shifting by performance of the post-pandemic era. So what the data drift exactly? So data drift occurs when the distribution of the input data in production is different from the distribution of the training data. So that's tracking this distribution is a good detection method. And the first detection method, it's a population stability index. It measures the change in the distribution of a single variable, and it's calculated by the binning the data and comparing the percentage of observation in each bin between the two samples. It's perfect for tracking of the key features and its performance over time. The next one is a Kolmogorov-Smirnov test, or KS test. It's a non-parametric test that compares the cumulative distribution functions over two samples. And the best way to use it is for numerical features. The last one is Jensen-Shannon tests. It measures the similarity between two probability distributions, and it's useful for comparing the distributions of the two categorical features. Let's talk about the resolution, and the first one is continuous monitoring and retraining. So that's the most fundamental line of defense. By implementing the automated pipeline that continuously monitors the data drift, we can integrate it into our machine learning pipeline. And as soon as the data drift detector alerts any problems with our features, we can initiate the model retraining. The next one is adaptive learning. For some model, it's possible to use an online learning techniques and update the model parameters when the new data arrive. And the last one is domain adaptation. It's a more advanced technique that attempts to adapt the model training on the source data distribution to a different target data distribution without relabeling. Now, let's talk about the concept drift. Let's go back to our self-driving car example. And it's known fact that the red octagon signal with the letters stop mean that car must brake. But what if tomorrow society will decide to change it, for example, and prepare of stop meaning, or just speed up to clear the intersection? In that case, input feature has not changed, but the relationship between input features and the target variable has changed. This is an example of the concept drift. Talking about the real life, the fraud detection models, they're in a constant battle with the concept drift. So imagine that you train a model to predict the fraud transactions. And for example, now your model learned that transaction from the specific countries at a specific time, it's likely a high risk. But fraudsters, they can adapt. They might start using the VPN, pretending that they're from the low-risk countries, or they just can switch their attack times. So that's a really aggressive example of the concept drift. The concept drift, it's usually more challenging to detect, since we don't only need to look at the input data, but we also need to track the model performance. It's offline and online metrics like accuracy, F1 score over time. And that actually would be the perfect first detection methods, performance monitoring. We want to monitor the main performance metrics of our model, like accuracy, precision, F1 score, and on a labeled validation set. And as soon as we will see any sustainable drop, it will be the signal of the concept drift. The next one is adaptive window. It's an algorithm that maintains a sliding window of recent data. So that window automatically grow or shrink the window size when the statistical property of the data within the window change, signaling the drift. And the last one is a drift detection method. It's when we want to monitor the model error rate, and as soon as that model error rate exceeds a certain threshold, it's a signal of the concept drift. Now let's talk about the resolution strategy. And the first one is online learning. So we can use the models that can update its parameters incrementally when new data arrives. For example, algorithms like stochastic gradient distance are naturally suited for this. Or we can use ensemble methods. Ensemble methods is when each model is trained on a different window of the data. And ensemble can give a higher weights to the recent data and, for example, phasing out an older and outdated concept. And the last one is trigger-based retraining on the label data. This is a most common industry practice. It's when monitoring tools detecting any problems, any significant drops in our model, we will initiate the model retraining. Perfect. Now let's move on to the label drift. And so imagine that you are working on a model that predicts that user will add an item, will click the add item to the shopping cart button. And usually probability of that event is around the 5%. But now the Black Friday comes and the input feature is still the same. And user intent is also the same. They still want to buy something. But now the probability that the user will click add to the cart button is around the 20%. So this is where the proportion of the model output changed. And this is an example of the label drift. Talking about the real life, let's think about the economic recession and loan defaults model. For example, model built to predict the loan defaults. And model training trained in a stable period of economic can set the default rates as, for example, 2%. But let's imagine that unexpected recession hit and unemployment skyrocket, and suddenly the actual default rates jumps to the 10%. Model still celebrated on a 2% rate, but now it's completely underestimate the risk across the board, and it can potentially lead to the massive financial loss. This is a label drift in a nutshell. So talking about the detection, it's more similar to the data drift, because label drift can be detected by the monitoring of the distribution of the target variables itself. So again, we need to look only on the specific target values. And the first method is monitor the class distribution. It's a most straightforward way. We will track the proportion of each class in our labeled data over time. A significant change in any amount of objects of specific class might be a signal of a label drift. The next detection method is a chi-square test. It's a statistical test that can be used to determine if there is significant association between two categorical variables. And it also can be to compare the distribution of labels in a reference window in comparison with the current window. And the last one is track prediction distribution. For example, we can check the proportion of the amount of the positive class. For example, if model used to predict the 5% of positive outcomes, and now it predicts around the 15%, it could be noisy, but still an indicator of the label drift. Talking about the resolution. So the first one is recalibration. It's the model output can often be adjusted post hoc. for the new class distribution. For example, by using the techniques like plot scaling or isotonic regression. It can be used to recalibrate the model probability scores to better match the new reality. The next one is performance weighting. So during retraining, we can assign during retraining, we can see the difference in the distribution of the class labels. For example, minority and majority of the objects of the targets of the classes. And we can use the weights to adjust, for example, the higher weights to the minority and lower weights to the majority to balance our data. And the last one is cost-sensitive learning. When we train our model, we can use a specific learning algorithm which can penalize the more costly errors for model more heavily. This can make the model more robust to change in a class distribution. Good. Now let's talk about the failure mode 4, feature pipeline degradation and train source skew. So imagine that you're a chef working on the prize winner, and now recipe is ready and it's flawless, and you send it to the chain of the really busy restaurants. And for example, one restaurant is using different ingredients, unsalted butter against the salted. Another one has 20 degrees of oven, and in the third one, for example, key ingredients is simply missing. The recipe hasn't changed, but the ingredients and the cooking environment has been compromised. This is an example of the feature pipeline degradation. And in the reality, the best example would be the Google diabetic retinopathy AI. So once Google developed a state-of-the-art deep learning model that could detect the diabetic retinopathy by using the high-quality pictures, and the model performance was on par with a real human ophthalmologist. And as I said, in the lab they used high-quality, perfectly captured images, but in the reality, when the model was deployed in the clinic in Thailand, its performance dropped, because the nurses working in busy, poorly lit conditions often capture images in the very lower quality, so lead to the model misclassifications. This is again an example where the environment has been compromised, leading to the feature pipeline degradation. So talking about the best way to detect it, we need to consider different issue types. For example, the first one is a data quality issue. It's when the data itself is corrupted. For example, some column can have different data types or increased amount of the null variables, or null variables can even be unexpected for this column. It's where the data validation framework like Great Expectation or DQ can help us. This tool allows us to define a suite of expectations for our data. For example, expected amount of the null variables or expected mean in the certain threshold. This check will run every time that the new data arrive. The second issue type is schema changes. This is pretty common for big corporations where multiple people involved into different part of machine learning pipeline. For example, multiple people responsible for the feature, lifecycle, model lifecycle, etc. And this is where, for example, the schema has been compromised. For example, column was renamed, removed, or the data type changed. And it's where the schema monitoring can help us, and our pipeline will automatically validate schema and prevent the corrupted data reach the model. And the last one is train source skew. It's when we can have a feature value from a specific pipeline or from the specific part of the code. And this pipeline or part of the code can use different packages, for example, leading to the different value of the feature. So it's where we want to log inputs and outputs of the training and of the same data, but on the different environment, training and the production. And if training environment and production environment and with the same model produce different responses for the same data, this is a signal of the feature pipeline degradation. So talking about the resolution, the main resolution here would be the feature store. It's a gold standard, industry gold standard. So the feature store is a centralized system that manages the definition, computation, and serving of feature for both training and environment. And it's programmatically eliminate the class of problems. The next one is robust data validation. It's, as I said, we can integrate the data validation checks directly into the machine learning pipeline, preventing the bad corrupted data will reach the model and cause any harm. And the next one is data contracts. It's when we want to establish the formal agreement between the different teams working on a machine learning pipeline. For example, to have an agreement in a schema change and prepare the model for any feature changes, let's say. And the last one is a containerization. It's basically packaging our model and its dependencies, ensuring that the training and production environment is the same. Now let's talk about the last one. It's feedback loops and bias amplification. So let's think about the popular music streaming service. And its recommendation algorithm suggests you a few rock songs. And yeah, you like them. And now, in return, the algorithm recommends you a few more rock songs, and you like them as well. And now, algorithm thinks that you are a die-hard rock fan, and it's completely ignoring your potential interest in jazz and classical music. So the model created a reality by amplification its initial bias. The real-world example is a compass recidivism algorithm. So the compass is a correctional offender management profiling for alternative sanctions. It's a tool that had been used by the United States justice system to predict the likelihood of a defendant reoffending. And 2016 investigation revealed that the algorithm was significantly biased against the black defendants, flagging them as a high risk for the future crimes at nearly twice the rate as defendants with a similar history. White defendants with a similar history. The defendant flagged as a high risk and received a longer sentence, be denied parole, and faced with the heavier police, and all of that led to the higher likelihood of the future arrest regarding their individual actions. So this is where, again, the feedback got broken. So talking about the detection, usually feedback loops occur when the model output, y from t, let's say, times temp, influence the state of the world that will be used as an input for the model retraining, x t plus 1. And yeah, so we can use several detection methods to prevent it. And the first one is diversity and exposure metric. For example, we can quantify the variety of prediction in the model is making. For example, for the recommendation system, we can ensure that number of unique items, we can ensure that there are specific unique items recommended over a period. Or we can use an A/B test. A/B test, like, for example, run a small percentage of a user that use a non-personalized version of our software and a personalized model recommendation. And if we can see that the behavioral of the model-driven group has changed, so it can be a strong feedback loop in a place. And the last one is a causal inference techniques. So we can employ more advanced statistical methods to try disentangle the model's influence from the user organic preferences. It's, for example, techniques like uplifting model can help estimate the true persuasive effect in a production. It can be used when, for example, we cannot use the A/B tests. So talking about the resolution, the first one is exploration strategy. For example, we can extensionally introduce some randomness into our recommendation model. So this will allow the model to collect data on a wider range of possibilities. For example, if we recommend the batch of 10 elements, 1 or 2 elements could be randomly selected. The next one is positional debiasing. So when we talk about the recommendation system, usually they can return ranked list, where the higher elements usually has a higher probability that the user will click on them or like them. And the model can misinterpret it as a stronger preference. So that's where we want to add some positional debiasing techniques, so telling the model about the position of the item in a recommended list. And the last one is fairness constraints. It's during the model training, we can introduce the mathematical constraints to ensure that the model prediction satisfies a certain fairness criteria. For example, if we work on a loan approval model, we can just use statistical concepts, statistical similarity across different demographic groups. Now we covered the main problems, and we can think about the proper way to set up the monitoring. And yeah, so deploying a model without the monitoring is like flying on a plane without an instruments. We are simply blind to any changes, and it also can make the debugging a nightmare. So the first thing that we want to cover with additional monitoring is model performance. We want to track the business metrics and the model performance metrics, online and offline model performance. It's recall, F1 score, accuracy, and as an online, for example, CTR or revenue lift. The next one, which we want to cover, is data health. It's statistical integrity of the data which we feed to our model. This is our early warning system, and we want to track the PSI, KS statistic, null rates, data types, schema changes, min, max, all of that type of changes in our features. The last one is system health. So system health is an operational performance of the whole infrastructure. And it's not only perfect for debugging, but it's also perfect for understanding the bottlenecks and plan our future optimization. So we want to track the inference, latency, throughput, error rates, CPU, GPU, and memory utilization. And yeah, you don't need to implement anything from scratch. There exist a lot of open source tools that can provide this functionality out of the box. For example, in open source, it's tools like Evidentially AI, NaniML, and alibi detection. They provide frameworks for detecting data drift, concept drift, and model performance degradation. And there also exist a lot of commercial platforms like Ylabs, Fiddler AI, Arise AI. They not only offer you end-to-end observability platforms, but also can allow you to integrate your model into the more broader machine learning ecosystem. Now, when, for example, we have a proper detection, and let's say that our detection framework just alerting, and so we need to understand what we want to do, how we want to retrain our model. And there exist different strategies. And the first one is a time-based strategy. It's basically the schedule-based, for example, when we want to retrain our model on a daily, weekly, or a monthly basis. And it's, on the one hand, it's simple to implement and it's predictable, but it's also highly inefficient and waste of the resources, because not always we need to retrain our model. So we can think about the performance based on that case. For example, we can retrain our model once the key performance metrics drop. It's directly tied to the business variable, and it's retrained only when we need it. But unfortunately, it's a reactive and not proactive approach. So the model already been underperforming, and it's already produced some losses. Okay, in that case, we can think about the drift-based approach. It's when we can retrain the model once we can observe any drift metrics, any feature drifts. For example, by tracking PSI or KS statistic for key features. And this approach is proactive. So we can trigger a retrain before the model performance drop. But it also can be noisy, and not all data drift leads to the performance degradation. So instead, we can use a hybrid approach, and it's a recommended approach. It's basically a combination of multiple triggers into more sophisticated policy. It's a more robust and practical approach, and it's balanced the pros and cons of the other methods. But unfortunately, it's also more complex to design and implement, and it requires a lot of adjusting of the multiple thresholds. Yeah, talking about the best practicing for building our machine learning pipeline. The first one is design for drift from day one. So do not treat your monitoring and retraining as an afterthought. The architecture for detecting and responding to drift should be designed in parallel with the model itself. The next one is maintain training serving parity. So we need to ensure that we are using the identical code and libraries for production and training environment. The next one is gradual rollouts. So that's not a secret that never deploy your model directly to 100% of the traffic. Just deploy it to the low amount, for example, 5% traffic, and monitor its performance. And once you ensure that the performance of your model on pair or even better than the production, in that case, you can roll out to 100%. The next one is instrument for feedback. Model performance can only be measured if you have a ground truth. And you need to design your system to collect the feedback for model's prediction. It's also helpful not only for the understanding of the model performance, but also for the future improvement of the model. The next one is document everything. That's when the future you will thank you. We need to track everything, model cards, data lineage, decision logs, everything that's possible. It's not only helpful for understanding the problems with the pipeline and monitoring of the model machine learning pipelines without proper logging, it's a real nightmare, but it's also helpful for understanding of the bottlenecks and future improvements. My final suggestion is, the first one is stop thinking of the machine learning as a project and start think about it as a product. Different part of the machine learning pipeline has its own life cycle, features, models, even infrastructure. The next one is an invest into the MLOps. So we already talked a lot about why we need to add additional monitoring to our models and testing the model performance. And the last one is foster a cross-functional culture. It's data scientists, machine learning engineers, software engineers, and product managers. They all must work together to build and maintain this complex system. Yeah, that's all from my side. Thanks a lot, everyone. Feel free to reach out to me on LinkedIn in case if you will have any questions.